Nailed it. All right. Homework assignment for today was to add arithmetic. Is that right? What did we? Oh, variables, and that. Okay, yeah. So we had a variable environment. But I think it was like with a caveat, right? So the variables, the first time you use them, they get created. We didn't have a data segment where they got created within that, right?
Yeah.
Okay. Fair enough. All right, so before we get into that, I want to kind of pause that a little bit, and I want to start looking at the DOS API because we're going to want to implement some, if not all, of these guys. Probably just some, because some of them are going to not make a whole lot of sense for us in an emulator. So when I say API to you in general, what does that mean? What is an API in today's programming terminology?
Generally, it's used as a means of interaction between different systems that you don't necessarily have locally. So it's connecting to somebody else's API, use their system or whatever, or their service.
Okay, so fair enough. So effectively, it's here is a private enterprise, right? So you mentioned like something like a service, and there are aspects of the service that should be exposed publicly or for pay or something like that, and they are going to expose those elements to somebody through an API without giving them full access. So as an example, my wife just got these new really expensive Philips light bulbs that like plug into your router. Like they're Wi-Fi light bulbs. You know what I'm talking about?
Yeah.
Hue, Philips Hue.
Yeah. Margin is like 20.
Yeah, there's $200 light bulbs for 3 light bulbs.
Yeah. Why?
Yeah.
Because they're pretty colors and you can control them with your phone.
But so keeping this with what we're talking about, the idea is that they're compatible with something called HomeKit, okay, which Apple has an API that when these things are on your local network, they expose some of their functionality through to HomeKit, and then we are able to use HomeKit to make the lights do different things at different points in time. And the lights have a set of features that you are allowed to manipulate on them. And then I'm sure there's some aspect of the light that we don't have control over, like how much electricity we allow to flow into the light or something like that, to make it explode and that kind of stuff.
Make it explode.
You would definitely be doing that.
Not for $200 for 3 bulbs. Those are expensive light bulbs.
Oh, is that with the discount or without the discount?
I think it was 150 something with the discount, 160, maybe 160. Well, when you know somebody who works at Best Buy.
Oh.
But maybe still, that's ridiculous. And this is just to test them. I'm sure she's going to want to get like another dozen colored bulbs.
Oh yeah, the colored are a lot more expensive.
These are the colored ones.
Yeah.
These are
That's
3 for.
Right. That's why I'm saying the non-colored ones are like $50 less or something.
Yeah, you can go over to Home Depot, and you can get a 24-pack of LED light bulbs that are supposed to last for 1,000 years.
Supposed to.
If we get a 10th of the lifetime out of them, things will be great. And 24 of them is like $14 or something like this. Do you really need to control your lights with Wi-Fi?
Not until it gets cheaper.
It's like,
those
whoa.
people that like super like.
I want to be able to go into
up their house and it's just like I'm turning off my lights from vacation, like with the commercials.
You could like buy a Raspberry Pi for each one of them.
Yeah.
Set it up.
Now the thing is yeah. Plus, it wouldn't look as integrated. You'd have these ghetto things wrapped around every bulb.
With $50 for each one, it's only $150 plus $14 for all your light bulbs you want.
Yeah.
They're still cheaper.
Yeah, but it would be an eyesore in a hefty setup. But you're right. You're right at some point there. But
you could have it all hidden.
But you would think that this type of thing would be something that I would be interested in. But at some point, if I'm not lazy enough to like be all about this, then I think it probably should go away. I think it's okay to have to hit a light switch. That's
Yeah,
not that big a
you
deal.
go onto the clap on.
Oh, did they get rid of those?
Yeah,
They
just like
they
disappear.
still exist somewhere.
I mean, that's got to be before your guys' time.
Nope. No,
Really?
right when we were about teenagers.
Oh, really?
8
That
years
seems
old.
like it was forever ago.
It's just like, you know, the unhealthy. It's just like the unhealthy food thing. It's like
No,
the
they
view, it's
had-
like if I look at something and say I shouldn't eat that, I think you can take that to the bank.
When I had Night at the Museum, he had to make his snap instead of clap. That was his thing.
Oh, that's right. Yeah.
That was-
Okay, so when we talk about an API, we're talking about the magic tricks that are exposed by usually some sort of private system. So DOS being an operating system, and we're kind of looking at DOS through a very old school lens. We're trying to look at it through the 8086 lens. So DOS from many years ago. So you put yourself in the shoes of an early operating system developer, and you're going to say, here are the things that we need to expose to the CPU for them to perform operating system stuff. This is a list of the API. All right, so the instructions always move into the AH register. So we had already looked at the Hello World program at first day of class or something like that, or if it wasn't, it was second day, whatever it was. And we kind of saw a Linux example where we had to stage a bunch of stuff, right? So we staged the a command into AX. We staged I think the length of the string into BX, the string itself into DX, and then I think it might have been whatever it was. Then we also had the output stream that we wrote it to. So we staged 4 values, and then we interrupted the CPU, which says, operating system, I've put values where they need to be. You take over from here. Make sense? All right, and then the operating system went and did its thing. So to read something in from, that's for writing something out for that Hello World program thing. So we're going to look at just these first 2 initially here, but as we kind of flip through here, you see that we can read a character in, we can write a character out, single chars, okay, a single byte in and out. We can write a character to a printer. Obviously, that's something we probably would not implement, but one thing that we notice that's a difference between, and I mentioned this earlier, so Curcio will remember this, but the DOS operating system versus Unix type operating systems is that Unix type operating systems are POSIX systems. And that means that, among other things, that they treat everything as a file in a POSIX operating system. So that's kind of the telltale sign of a POSIX operating system, is everything's a file. DOS is, let's call it, more proprietary. That doesn't mean it's worse. It just means that they, everything's not a file. There's a difference for printers versus files versus writing to the screen versus reading in from the keyboard. Those are all different types of animals, even though they might be similar with each other. Whereas in Linux, being a POSIX operating system, all 4 of those things would all just be a file descriptor. So when we write these commands, you're going to have a more generic version of reading and writing, because you're going to have to say, where am I reading from and where am I writing to? So we have to give it more information. So DOS is simpler, and that'll make our life a little bit easier. All right, so we want to look at just these first 2. So let's start off with reading a character in. All right, so we load into AH, the command. So command 1 in the DOS API is read a single character in from standard input. And this is the one with echo. I think there's one without echo as well. But we'll just look at this one as a quick example. So we load into AH what we intend to do. And what it will do is, once we're done, it will put into AL the character that it read. We should be able to see that update. All right. So I have this open from earlier. Let's kill this. And I guess we'll just break most of this. Yeah, because I actually want to start this stuff again. It'll be all right. And then we'll do, I'm going to call this guy main just for the sake of whatever. Okay, so I'm gonna go ahead and let's just do this all inside of main for right now. I'll just have these other procedures in here, so I'll make sure I return at the end of main. All right, so we're going to move into AH1. So you can say 1 hex, just 1, doesn't matter, they're the same value. So we'll move into AH1. We intend to read something in. All right, then we need to interrupt the CPU, so we do an int 21H. This is the DOS interrupt. So this says interrupt the CPU with this code, which says transfer control to the DOS operating system. Okay, if you remember looking at the Linux hello world, assembly, the interrupt call is a different interrupt, so we're interrupt hex 80. Okay, so this is a 32-bit version of Linux, so a much newer assembly language than 8086. So we stage 4 values: the length of the string, the base address of the string, the file descriptor that we're going to write out to. So file descriptor 1 is related to standard output, which is our monitor. Here's the equivalent to our 1 in our example, except this writes out a string as opposed to writing out a char, but same thing. Well, we're reading in a char in our first one, but this is the API for the Linux operating system command that we're executing here. Then we interrupt the CPU, passing it this, which gives it control to the Linux operating system. Make sense? So we're looking at the DOS version of that. Okay, so we'll read something in this one, our API says this guy has echo. So read character from standard input with echo. All right, so let's watch this guy happen. So we'll go ahead and emulate that. Oh, I have stuff down here that's based on things from the data section that I have deleted. So let's just kill all of this. All right. I'm just going to go ahead and run it. So it's waiting for user input. I'll put in an S. Oh, so it either doesn't echo by default or... Oh, hold on, let me change the font here. Can I make that bigger? Well, that's interesting. Is this thing like just crashing a slow death? Oh, there it is. It's still, it says it's still cooking. I don't think that's still cooking. All right, let's kill it. Am I able to copy this before I? No, I'm not.
Mine totally worked.
It should work. Or it should crash.
Clearly.
One of the two. Okay, so we're back, and let's go ahead and run this. Put it in an S. Oh, it did it again. Yours is echoing, right?
Yeah.
Yeah. Program has returned control to the operating system, so that's the interrupt.
You have to give it input.
I did.
With the S?
Yeah. That's a single character. Yeah. But it should echo a second one. You should see SS. That's what you saw in yours, right?
No.
Oh, you did. So you just saw a single S.
Well, isn't that?
It read it. No, see what you're seeing here is the S I typed.
No, that's the output.
I don't think so.
Try it again.
Well, there's no way to tell it.
Yeah, see? Wait, did you just type? No. Go ahead. Exit out. There. Restart it.
Yep.
Okay, so hit S.
Okay.
Okay, it didn't. What happens is, see the change font?
Yep.
Next to it, there's the 0 of 16. So restart it.
Okay, I get what you're saying. So I'm assuming that it read in my S when the reality is this was the echo.
Yes.
Okay, so on input through this, it doesn't show me.
It writes it down where next to change font, where the 0 of 16 is.
Okay.
Like, so when we were doing the Hello World thing the other day, or for the other class,
Yep.
we found ones that you could type like for input and stuff, where you type in Hello World, and then it would take in your input and then print it out, and that's where it would input at down there, and then.
Oh, you would type it in down here.
Yes.
Keep hitting letters. Keep hitting letters.
Yes.
Yeah, there they are. So it shows so it takes the first one, steals it, and then that's I guess what the buffer is. I guess this is a 2 byte buffer.
All right, so this is my input,
Mhm.
and this is the echo.
Yep.
But since we only read in one value, okay, that's fine. So that's how the terminal works. That's not every terminal, by the way. That's how EMU 8086 seems to work. Okay, so that's reading in a single character. If I want to write out a single character, now let's see, is there a read character without echo? So here's read. It does not. Oh, here it is. Direct char read, no echo. So this is move 6 in to AH. Now one thing I want to see here on this guy is I read in, did I type in an S this time around? Let's just run it again. So there's my S. Notice that in the low AL, I have a 73, which should be the ASCII value of a lowercase s. The hex representation of that. Is that right? Because that's how it should represent it. It should be an 8-bit representation of the character lookup of S on the ASCII table.
Yes, that's correct.
All right, so that's what got loaded into the low there. Let's see how the direct console input without echo works. So we're going to load into AH a 6. So let's kill this. Kill this. Load in a 6 and not change anything else. Emulate. We'll run. There's our S.
I think it just immediately skipped past the read.
Looked like it maybe was 2 parameters we had to load. So DL FFH. No character available. Oh, that's direct console input. Here's direct character input. Is 7, not 6. Now this guy should work. So there's my S, no echo, but we see that that character was read in and stuck into AL, the lower half of my AX register. Make sense? So that's how that guy works. And what we're going to go ahead and do is we're going to move that into a procedure. And then we're going to look at So we're going to say read char. It's going to be a proc. And then np read char. And then inside here, we'll do this. And this guy will call read char. All right, so I just moved that logic into a function. We'll call the function from up here. It'll move the appropriate command into, so we're kind of implementing our own, more human readable version of the DOS API. So we'll move 7 into AH, we'll interrupt, tell the operating system to take over. We know that we can look for our answer inside of AL following this guy. We could choose to have this guy do something more. Maybe it puts the answer onto the top of the stack or something like that. Have we talked about the stack much in here? Okay, so we'll look at the stack a little bit.
I know.
You could eat your sandwich faster. Is that a roast beef?
Oh, it's turkey or ham.
Oh, that's not better.
You gotta get the,
Either of those answers. It's turkey.
you gotta get the JJ.
BLT?
No, the gargantuan.
Yeah, the gargantuan's all right, but I think the best sandwich there. You want a fat guy pro tip? Okay, so best sandwich there, you get the Italian Knights Club. So it's basically an Italian hoagie with extra Vito meat. That's a giant, it's basically gargantuan size Italian hoagie from Jimmy John's. Because I think the gargantuan has too much other meat.
This, okay?
Well, I can barely eat that because it's a boring sub. Like, I don't think like roast beef and stuff makes sense in the gargantuan. It's fine, but I just don't think it makes that much sense. So, pro tip. Italian Knights with extra Vito meat. Okay. So we'll call read char. This guy should pretty much do the identical thing that we just had. I'll go ahead and hit run. We'll put S there. It loaded it into the low of that guy. If we want to go ahead and see the stack, what I can do here is I could, well, watch. Have we seen call in here either? All right. But we're following it pretty quick, right? This is like rocket science. All right, so I wrote a procedure, I'm calling it a procedure. But an interesting thing that happens here is when I do that, just reload it, we'll step through it here. I'm gonna go ahead and show the stack. And when I do this call, step over it, you notice we get a value here at the top of the stack. Now that value gives us, it's the memory offset address of where we need to go from the beginning of the code segment to the next line, which is going to be this line right here, upon this procedure being done. So on the top of the stack, we've thrown a value that lets us get back to where we left off. That makes sense? We went through this exercise in the 325 class, but understand that this value, this 105, this is not an offset in the way these numbers are read here. Instead, let's see, can I make this any bigger?
Close up the stack.
Oh, that's what keeps me from being able to, oh, I just can't scroll, that's it. Okay, so code segment starts at 700. All right, so this is the beginning of the code segment here. It's 700, sorry. My next question is going to be
70, 60, 50, 40, 30, 20. Can you just type it in at the top?
it's possible.
Is that 700 or 7?
Nailed it. All right. So yeah, this guy is an offset off of that. So this is 700 base address. So offset 0, offset 1, offset 2, so on and so forth. All right. So this guy, where's our top of the stack? This is an offset of 105 from the base address of CS. So our code segment, this guy right here, is given a base address. If we think about organization, and this is something we depending on how in-depth we get with our emulator, we can implement if we wanted to, but imagine having, put ourselves back in 1980 when we have a machine with a limited amount of memory, and you need to be able to write code like this for it, all right? And, among these other sections, we can just assume there's two sections in our world. There's a data section where we put our variables, and there's a code section where we put our logic, all right? That data section gets read in first, or data segment is what they're referred to, what they're called. So that data segment gets called first to load any variables into our environment. So this last assignment, we created like a mini variable environment, right? So when we first hit this data segment, those are the things that get loaded into our variable environment, whereas in our assignment, we just magically had the guy show up there because we didn't have a data segment yet. Well, that means that when we write this, whoever implemented this, so Intel people, they're going to have to create a chunk of contiguous code and call that the data segment and say, this is now protected space from the code segment, which means that we have a legitimately limited amount of space in the data segment. So we're limited on how many variables we can define by the amount of memory. We're also relatively inefficient because we're arbitrarily picking especially in the early computers where memory was really limited, right? We're arbitrarily picking an amount of data for our data segment, an amount of memory for our data segment. Let's just say it's 1K, right? So 1K is our data segment. That means that all of our variables we might want to create has to live within 1K in that data segment. Now, understand that that's not the values of those variables. That's the variable declarations themselves. All right. So if we put something up here like, I kind of hate the fact that it won't just, like, shouldn't it just like kill off like, oh, you want to type over here? Okay, let me just shut this for you. It should do that, I would think. So I might say something like message is a DB. Let's just leave it like that. So I've defined a data byte named message. This is a label. So the size of this guy is a label. So we're gonna, this guy's gonna have size associated with it. So this takes up 1, 2, 3, 4, 5, 6, 7 bytes. 8, 9 bytes. So 9 bytes out of however big my data segment is taken up with this message right here. And there's a space in there, so that's technically going to be a byte, but all that stuff, my variable declarations, will live inside of that data segment. When we process the data segment, we actually go and create those variables in actual memory. So we have 3 different sections here. We have where data is defined, where our variables actually live, where the values actually live, and then where our lines of code live. And I guess the fourth thing would be our API associated with the processor and the operating system. Kind of very related, but 2 separate instruction sets, right? The 8086 Intel architecture has its own instruction set. And then on top of that, we have an API associated with the operating system that was designed with the 8086 in mind. All right, so those 2 guys can work together. So we become limited on this, and this is also why, if I go ahead and start this again. Oh. Oh, it's because I didn't give it a value. Do something like that. Would be okay, I think, for starters. Question mark just means I'll set the value later. It's, non-initialized, something like that. Okay. So When we start this up, notice that CS has a value in it and DS has a value in it. And notice that CS and DS actually have the same value in it. Now we discussed this, I think it was the last class. I'm 97.25% positive. We talked about the difference between tiny, small, large. I think I brought a web page up that talked about the differences between those guys. Assembly model. Just go here. Huh? Let's just go tiny. This will probably give us our... So small, the code and data segments are different and don't overlap. So we have 64K of code and 64K of data and a stack. So this is in the small model. Actually, what's interesting there, though, actually is these are the same. So this is actually following what's called tiny. I wonder if this is relative. Small as it relates to 8086 may have followed the other, because this is Turbo C++, which is significantly newer than 8086. Let's do 8086. Yeah, I think this is the one we had looked at. At least I thought we had. Small, all code is placed in one physical segment and all data in it. Oh, no, I think this is an 8086 one, which just means that the emulator is written funny. So really what it's showing here is the tiny model. So both the code and data occupy one physical segment. So all procedures and variables are by default addressed as near, which means near the beginning of where your assembler is loaded, by pointing at their offsets within the segment. So both of these guys had the same base address. So our data segments at 700, our code segments at 700, but then we have offsets off of those guys that tell us where the next guy is. So for instance, our instruction pointer is 100 offset from 700. So that's the next instruction that will happen. But what is interesting is that we have this set up as small, yet it's doing that. I wonder if we just arbitrarily make it large and see if the emulator does it differently, or the emulator just says we're just treating everything the same. Go ahead.
Is it because of the org 100H underneath it?
I wouldn't think so, because this has to do with stack. So let's switch that to tiny. CS, DS, okay. Okay. So small should give us two separate ones. That's what it's supposed to do. And this guy used to be stack, right? So that's specifically giving us a dot stack.
I don't think the 100H still is supposed to be there.
I think so.
Is small case sensitive?
No, I don't think so. I mean, we can test it, but I'm pretty certain it's not. CS, DS, okay. So data segment is at 700, code segment's at 721. So we have 21 bytes. Actually, no, that is. It must be just because of what we're using it for. So it must dynamically create the memory for this guy, which would be different than it would have been back in 1980. It wouldn't have dynamically generated that. If we switch this to, I hate that. We switch this back to tiny, then it should be the same again. CS and DS, yep, both are 700. All right, so those different models tell us, give us our limitation on how big our data segment and our code segment can be. Not that important if you're writing very small, trivial things like we're doing, but becomes more and more important as you're trying to push the hardware that you're working with to its limits, and you're playing this juggling game between the registers you have and how much memory is on board and all sorts of stuff like that. Okay, so we'll put this back to small for no good reason. All right, and then we'll read we already read our char, we saw that work. Okay, so let's go back here. So now we want to write something back out. So we just did this without echo on purpose so that we created a procedure to read a single char in. And now we want to write a single char out. Not a string, but a char. All right. Write character to standard output is 2. Click on that guy. So I write character to standard output. We load into, so we loaded it into AH, the thing we want to do, which is write a character. We load into DL, the character we want to write. Make sense? So we can load into, let's go ahead and do it out here. So we'll call read char. After read char, we know that the character we read in is in AL right now, right? That's what that guy does. The read char puts the character that we read in into the lower half of AX. All right, so now we want to move into AH a 2 because we're going to write a char out to the screen. All right, so I moved into AH a 2. Then we need to move into DL, the low half of DX, the character we want to write. And where does the character we want to write currently live? AL. So I'm going to move into DL AL. Yeah, AL. Did I type something funky?
No.
Yeah, so AH is what I want to do. AL is the location of the character I just read in. That's what read char does. No. AH is always where we load the API command.
Okay.
So we're performing magic trick 7. That's what goes into AH. And then AH has the side effect, if I go down here to 7, of putting the character in AL. That's where it stores its result. Yeah, we'll have the interrupt up there. So then we're going to have our interrupt to tell after we've staged everything we need to stage. All right, so I want to write something out. What do you want to write? Well, I need to move into DL what I want to write, and I want to write whatever is currently in AL. So I'll move that in there, interrupt, and then this guy should spit out to the screen. So the result should be what we saw for the original, which was with echo, right? But now we're doing it manually, I guess. All right, so we'll go ahead and run this. So there's my S, and it's outputted the output. It has outputted. Is that a word? Outputted?
It has output.
It has. Yeah, it's weird. Something that on Big Bang Theory they would argue about for 20 minutes. Have you seen that? Because you're wearing a Bazinga shirt. Have you seen that episode where Sheldon is trying to figure out the grammar of talking about things in the past, like have, has, had not, or something?
It sounds familiar.
Yeah, it was.
The past tense of output is outputted.
I got it right. It's pretty rare when I get something grammar related right. Yeah, I'm pretty proud of myself actually. Okay. Most bestest. That's right. Do it more better. More better, most bestest, right? All right, so let's go ahead and write a procedure for write char. So we're going to have write char proc, and then endp write char. Okay, and we're going to throw this stuff in there with a return. All right, so there's write char, there's read char, so I should be able to call read char, then call write char, and this guy should do what it's going to do, proving that those two guys work in and of themselves. Understand that we do have some coupling associated with these guys. We've had software engineering, right? What does coupling mean? Say, well, I give you an example. We do have some coupling right here associated with these two procedures. So without worrying about the word coupling for a second, what do these procedures have related to each other? What kind of requisite information do we need in order to make the two procedures work?
We need one to make the other one.
Okay, so read char has to do its thing first, right? And write char then, and so just take what you said one step further. Write char needs to know to look for its thing inside of AL. Okay, so it has a reliance on read char, but more importantly, it has a reliance on on how our DOS API functions work. So it's not so much that you need read char in order for write char to work, because we could just artificially load something into AL and write char would work, right? Yeah, DL, thank you. Well, actually, technically, what I said is correct.
Yeah, because we're moving.
Oh yeah.
I think we both were answering it correct for the same reason, but I was actually right.
No matters.
But I believe that you were right when you said it. Because write char happens to just take whatever's in AL and shoves it into DL. If we didn't do that, I could just arbitrarily put whatever I want in DL and this would work. All right. So when two things are coupled, that means that changing one then breaks another one. In I guess software engineering terms, you might say that that's an argument for making code as self-contained as possible, even if it ends up making your code larger, because you have less side effect when you do bug fixes and that kind of stuff. All right, so we have the ability to write a single thing and read a single thing. Okay, and let's just run this real quick and make sure all this stuff is copacetic. I'm pretty sure it's a word. All right, there's our.
Big word.
Is it? I have a PhD. I know a lot of big words. I have the best words. That's the Trump thing, right? Doesn't he say that stuff? I have the best words. It's going to be huge. All right. Now, I then want to talk about looping a little bit. So I'll give you a little foreshadowing so you can start thinking about this, because I'm going to have you guys break up into a couple of teams here in a few minutes to try to accomplish a task. We'll probably do it after our first break, but our first break's not going to be for like another 10 or 15 minutes because we kind of babbled.
Did you use the word copacetic in?
Copacetic?
Yeah.
I want to make sure that everything is copacetic. Everything is good to go, not having problems, not having errors.
The definition for copacetic is in excellent order. So
what he said.
What I said. Everything is, so I want to make sure everything is in order. Everything's in excellent
You
order.
have to realize
The word was used correctly.
You have to realize this is one of
debatable.
the best words he was talking about a minute ago.
this is
Who do you think Merriam-Webster called when they were writing their dictionary?
T-Pain?
T-Pain. Ooh.
I didn't realize.
Mr. T?
I didn't realize dictionaries could be auto-tuned.
Is T-Pain still a thing?
He is.
Like he still sings and stuff?
I would assume so.
Or as much as I don't listen to music, but I only know about T-Pain because of the I'm on a Boat song. So the only reason I even aware of his existence is that, plus I think that he had an app. Did he have an auto-tuner app for iOS? Yeah.
He did. Yeah, no, Little
still
Dicky
doing
just stole his
stuff.
set. Did anyone make you watch the free? What was that Little Dicky video where he did all the free stuff?
I don't even know who that person is. That's a person?
He's a Jew rapper.
It-
White Jew rapper. Little Dicky.
Well, now I'm interested.
No, what you're talking about.
You come on.
Well, I don't listen to any music,
Come
literally.
on.
I was.
Little Dicky?
was his
Well, all right, we'll deal with that at break. Let's let's keep Howard for. But so after break, what we're gonna do is we're gonna split up into two little groups, and it's gonna be a competition. It's gonna be a death match, so half the class will die.
we can't even split properly, so.
Does someone
Well,
get you?
huh?
Does one team get you?
Yeah, we can do that. But I'm only going to be mediumly helpful. So
Tim, so.
so what we're trying to do here, see, if we look at the API, okay,
Exactly.
and you're actually gonna end up getting the punchline from class earlier today, because in 325 today we were looking at an API call we'll look at later on, which is buffered input, reading things in a string at a time, right? Well, we're going to write our own version of that. Why use an API call that's already written to do exactly what you want when you could just write your own, right?
Isn't that exactly what we're not supposed to do?
It's way more fun. Way more. But it'll help us understand how this guy actually works.
He's a rapper, okay?
All right. So this will help us understand how it works. But in order to do that, we need to first understand how the loop command works to be able to do something some number of times. All right. So what I'm going to do here, and I think we have, do I have my 8086 instructions up here? I think, oh, it's this guy, right? Might as well. See. There's just a normal loop command. Oh, this guy.
Just
Loop.
Loop
Except,
add-
yeah, no, I thought it was, yeah, there. That's what I wanted. Okay, right, yeah, that's I didn't think it was spelled like that. All right, so this guy relies. So this is a command. This guy is not a DOS API command. This guy is an 8086 instruction set command. So what's the difference, Tim, between instruction 8086 instruction set command and a DOS API command? And which one is loop? Well, I think I asked the question all right. What's the difference between an 8086 instruction set command and a DOS API command? How do we differentiate the two? And then which one is loop? No. Which team does that belong to? Okay, if we have two teams, we have the 8086 native instruction set team, and then we have the DOS API team. And the DOS API team has a bunch of instructions, and the 8086 instruction set team has a bunch of instructions. How do we tell those guys apart, like shirts versus skins? And which team is loop on?
You're on the skin team, right?
I'm always on the skins team, whether I'm on that team or not.
Mr. Litton, you do not need to take off your pants to get this.
Yeah. Flag football gets interesting.
Tackle gets even weirder.
I saw how, like, in a kind of a slow roar, the room got the joke. Wait a minute. Flag skins, flag. Oh.
See, he does. He just puts the flags underneath the flag, like it's storage space, so they can't get to it.
You're gonna have to go in there after it. This is all recorded. So.
The other team are just getting ropes, like tie me down. If I don't come back, I'll yank 3 times.
It's just so slippery.
No. Okay.
So answer the question.
It's part of the 8086.
Okay, and how do you know?
Because it's not setting up it's not using that API interface of loading something into AH.
Okay, so just upon looking at it, it appears like it's not following the DOS API
Right.
pattern of loading crap into AH and stuff, and also it's on the screen with the white background instead of the yellow background.
Exactly.
Okay, so
it also
but,
says 8086 instruction set.
oh, does it? Did you actually read that, or I'm hoping you were just too dumb to do that?
I'm still recovering mentally from those images of flag football.
Well, you had a chance before that thing.
It actually reminds me. It reminds me of something. This was early days of the internet. Yeah, early days of the internet. I gave some speech and I was pretty young, and I gave some speech in a class. It must have been
They pay you for this speech, or is it just?
no, it was like for a
Oh,
class for a class. Yeah, it was a student. So this is probably 1997 maybe. And back then, internet sites were very different than they are today in terms of the URLs and stuff like that. And so, and you had this up and coming kind of like porn taking over the internet type thing. So I handed out these slides for this class, like a, you know, a printout thing, and all the content on the slide was completely benign. You know, it was perfectly reasonable content, like given information, but the URL at the top that printed, because you know how you like now I think by default is the URL turned off. It doesn't print the URL anymore, but it used to be on by default. Okay. Was not benign. Okay, I'm handing this out to teachers, to all the students in the class. I mean, I don't even remember all. They had a lot of really great words that were not classroom appropriate. I'm handing them out to everybody. Nobody ever said anything to me. I found it myself later on, like, where did this come from?
Like,
It was like all porn stuff, you know, like words related to the porn industry.
how exactly did that get on?
I have no idea.
Maybe doing some research and
Yeah.
a little intensive.
Yeah. So I don't know. Like now, you would know if you've stumbled onto a questionable site, right? Well, back then, you know, we didn't have Google, so your search engines people would sometimes host legitimate data on sites that looked illegitimate. So I don't know. It just reminded me of that with the thing at the top here. All right. So in any case, we want to look at the loop command here. So loop looks at the CX register. So CX is a 16-bit register, and we load into it a number, and this guy decrements down. Well, it would be us to decrement it. And so it keeps going until CX is 0. So it effectively keeps jumping to the label over and over and over again as long as CX is not equal to 0. All right. So down here, we would, for example, move into CX5, start our counter. We want to do something 5 times. Okay? Then we create a label. So a label is a point to which we can jump within an assembly program. We actually already have some first-class labels in here that happen to be procedures. So let's call these super labels for lack of a better term right now. So main would be a super label. So instead of just having a normal colon after it, we've defined it as a procedure, which makes it do the whole put something on the top of the stack thing to get back. It does the special thing that we saw earlier. So we create a label, and so we might print something. So in this case, you know, they've created a function for printing stuff. So we might print something and then call loop on label 1, and we're going to do that over and over and over and over again as long as CX is not 0. That makes sense? And as part of the loop command, loop decrements CX. Okay, so we want to do something in this case. Let's say we want to do something 5 times. We want to read a char, write a char 5 times. So we'll say move CX 5. Then we'll put a label in here. So we're going to say, we'll call this guy read write. I expected that first tab to be a more aggressive move. All right, so read write, we'll call read char, call write char, and then we will loop read write. Okay, which will spin us back up to read write over and over and over again until CX decrements to 0. That make sense? So this allows us to loop 5 times. Seems to be going over and over and over again.
That happened before you did the loop thing. You just didn't keep hitting buttons.
Happened. What do you mean it happened before I did the loop thing?
Like you could, it would just keep going through read and write.
Well, it shouldn't have done that. So you're saying if I take the loop thing out, it'll just keep doing that automatically?
If you take out loop and read write,
Yeah, so if I move it back to that,
yeah,
What's gonna happen?
it just keeps going.
You're gonna return. Do you have the return there in yours?
oh, he's right, it does keep going.
Why isn't it returning?
That's a pretty reasonable question. Oh, I wonder. Here, I'm going to switch this back to that org thing. Isn't it just org, not .org? Like that? Because I have a feeling that that puts this thing in a different mode. I'm going to try it like this. Yeah. Let's look this up real quick for our own sanity. Assembly org versus stack.
Wait, what? Bad, David. Bad.
So it looks like org sets the base address of everything and relies on the other addresses being set dynamically, where .stack is just setting the base address of the stack segment, the stack itself. So they're doing different things. I'm not sure I'm totally happy with that explanation, but let's roll with it.
Ask Stack Overflow.
That should not work. Okay, good. Cannot.
Stack reserves 100 bytes. Word sets the current address to 100.
Correct. So stack is related to just the stack segment.
So could you have both?
I'm thinking yes. So I think
Would you want to have stack first though, right? So that
I don't think it'll matter.
that's probably true.
So this would be stack 100H. So this will give us a stack of size 100. This gives us an organization, a base address of 100. Yeah, so we were using them as replacements and they weren't. Okay. But when we didn't have org here, the evidence was that it just kept spinning through and through and through and through because it didn't have a base address. Let's take that out and let's just walk it and see what it does as we're walking through there. So we'll single step, put in our S, single step, single step, single step. All right, there's the output. I get to see where we're at in the code. So there's our return there. Okay. When we hit return here, it immediately just jumped back to the top of the program. So return must go to what it believes the beginning should be, and without a base address. Well, actually, interesting thing might be where is. Let me reload this. Segments at 721, instruction pointer 0000, step. I want to see what happens to the instruction. Oh, I gotta enter. Oop. Good. Instruction pointer's at 3. Now it's at 7. Okay. Now we're back to there. Instruction pointer's at 6. When I step again, it goes back to 0. So the instruction pointer is what's resetting. Whereas if I have org 100h, and we run that, let's look at what the instruction pointer does. Instruction pointer starting at 100 instead of at 0. All right, so that's where the org starts our base address at. Walk. There's our S, step. Let's drag this out of the way. Step. So we write it. There's our output. Step again. Now we're at the return. When we hit this thing, instruction pointer goes to 0 and we're done. So at 0, we don't have instructions. At 100, we do have instructions. When we don't put an org in there, it assumes everything's at 0, and it starts your code segment there. So it's the question is why would anybody not want to put? I guess the advantage would be you don't need this if you're not going to have any of these segments, and all your code is just going to sit in here. You choose not to organize it in segments. You just have it linearly go through your code, and then you would have to rely on DOS to kill the program. So you'd have to use, there's a exit API. Forc to have the operating system kill the process so it's no longer scheduled on the CPU. That would do it. All right, so we'll leave org in there for now, and now let's go back and do our loop thing that I took the code out for, but it wasn't that much code. All right, so we'll move into CX5. Then we'll call this guy read write. So we'll put a label there. A label's just a word with a colon after it. And remember, by default, assembly instructions happen linearly. So it's going to go from here to here. Labels are skipped. So it's just going to drop right down to that next line and go. So this guy isn't handled. This guy might as well not be there. It might as well be a comment unless you're using a command like loop or one of the jump commands that take you to a label to kind of reset stuff. All right. So we'll call read char, call write char. Then we will loop read write, telling it what label to jump to.
So sounds like the reason why org needs to be in there is so that the return command can return to the
proper place.
Right. Because otherwise it's set to the 0. So it'll jump back to 0.
Right. So that's what I was saying is if you didn't have the org there and you were just going to not have segments, you were just going to have your whole program just in one body of code, then you're jumping back to the right place by default.
Yep.
But because we have segments here, org tells us where the base address of our code segment is. And the instruction pointer, when it zeroes back out, you want it to zero out at the end of the program, which would be up here where there are not instructions, as opposed to zeroing out at the beginning of the code segment. So if code segment's presumed to be at 0, 0, instruction pointer goes to 0, 0. All right, so this guy should call read char, should call write char, then we should loop read write, and this guy will spin back up to read write, and this should do this a maximum, well, exactly 5 times, because loop should decrement this itself. All right, go ahead and run it. Run S2, 3, 4, 5, and it's done. Make sense? All right, so we read things in until our, we read things in until our loop ran out of stuff. Now, I want to go back in here. Let me close a couple of these guys in the middle. We're good. Okay. And I want to look at the compare command. Okay, so there is no result to compare other than flags being set. All right, so we can compare 2 values. So for instance, compare or move into AL and BL some 5s, compare AL, BL. Both of those guys are 5, so the 0 flag will get set. All right, we'll get set to 1. Now, we can try to interpret those, but we also then have some jump commands that do like jump if equals, jump if not equals, jump if not 0, things like that, that know how to interpret these flags. All right, so what we want to do, just kind of as a precursor here, we want to keep reading things in until the user enters a carriage return, presses enter. Just real quick here, I'm going to go ahead and we're going to reload this. We're going to run. So we're going to look at AL here. So when I pressed enter there, AL read in a 0D. All right. 0D, 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 0D. Did it 5 times. So 0D is my enter command. And what is 0D in ASCII? 14? Okay. And what's 14 on the ASCII chart? Okay. So that is the symbol, the ASCII symbol associated with the carriage return. So we want to continue to read in characters over and over and over and over again until a carriage return is entered. That make sense? Then we know we've finished reading in the characters. Now we need to have a place to store those characters. Now we can give ourselves a maximum storage size, but when we come back from break, we'll start off with read in until, okay, which is going to require that you use the compare command. And just for completeness here, let me take another 2 minutes and we'll look at the flags for the compare command. So I'm going to come up here. So before I do this loop stuff, I'm going to go ahead and move AX5, move BX5, move CX6. Then we're going to compare AX, comma BX. Those guys are equal. Compare AX, comma CX. Compare CX, comma AX. So this should be an equal, this should be a less than, this should be a greater than. All right, we want to see what that does to the flags. So I'll go ahead and emulate this. we'll step one line at a time. Let me expose the flags here. So we'll move into AX, BX, CX, our three values. Now when we compare AX and BX, the 0 flag should get set. So there's our 0 flag. So when 0 flag is set, that means the difference between these guys is 0. That means they're the same. Okay? Now I'm going to compare AX to CX. So AX minus CX should be a -1. We'll single step. Let's see. Sign flag gets set. So if the sign flag is negative and the 0 flag is off, that means that the first guy was smaller than the second guy. Make sense? Then, if we step again, the 0 flag should be off, the sign flag should be off. That means that the first guy was larger. Make sense?
Sure.
All right. So let's take 10 minutes and then we'll come back and I'll put you into some teams